Okay, everybody. This is the week 3 Friday lecture, and what we're going to be doing today is basically just going over more week 3 material. We scroll down here to week 3. We will see that there's a reading and a homework, and we'll work on those. Also, there is a lab 2, which is due next week, and there's a video in there that you can watch that will walk you through it. Um, but before we get started on the week 3 material, what I wanted to mention was this website here, which I don't know how to pronounce it. I always say the word Replit because that's what it looks like, um, but that's probably wrong. Um, but this site, if you haven't used it, is a site for it's an online Java like compiler basically, and VM, that's virtual machine, that you can use for your labs and homework. So you don't have to install Java on your own computer if you're not able to, basically. And I've had a couple of emails from people telling me that they've had trouble getting Java installed and that they couldn't do their homework. But that's not an excuse because you can go to this website here, which I will, and I'll log out real quick. How do I do that actually? Like that. So when you come here, it's just going to look like this, um, and you'll have to sign up for it. Or if you're signed up, you'll need to log in. And I just log in with my Google account. That's the easiest for me. But you can use you can just make an account here if you want to, if you don't like the options that are here. But I'm going to just continue with Google and sign in. And you get a page like this, and you can create Java projects or lots of other programming languages as well, just by finding where to create a project. There's a link up here, and there's another link down here. That's what you're looking for to create a project, one of those buttons. And when you do that, it says template, and you can search. So usually you would just search for Java if that's what you're trying to do, and then pick the one that just says Java. These other ones are not generally going to be what you want, but later on or in other programming classes, maybe you want those. Anyway, we're just going to pick the regular Java template over here. Oops, I have to pick. And then over here, we name our project. Always name it something that makes sense so you can find it later. I would never be able to find unwelcome full ports, which is just the random name that we've got right here. And so name your projects with something reasonable. So like I could do this like week 3 Replit demo or something like that. Um, so you could call yours like lab 2 if you're doing lab 2. In any case, you pick Java and you name it and you hit create and you get a blank project here. And you can always do your work for the labs right here in the main.java. And when you need to download your stuff at the end, over here on the left where it says main.java, if you click the 3 dots, you can download your file. So that's how you can get the Java file to turn in. Anyway, so I'll just leave this open because we'll come back here. But I just wanted to mention that as this is a way that you can do your homework without having to install software. So if you're using a Chromebook or an iPad or anything like that, like a Chromebook or iPad, or you just have trouble installing the software, you can use this. Okay. All right. That's all I really wanted to say about that now. So let's go back in here to week 3. And in week 3, we've got reading and homework. And it doesn't really matter which one of these I click on. They go to the same place. And in here, we were looking at the 3.3 material, I think, last time. And I feel like the last thing we did was one of these challenge activities. Yeah, we did this one, right? We did the one with tacos and drinks. Okay, so let's move on to the next section. Um, so this is just an example. The main things you want to keep in mind about this section 3.4 here is, we do want to understand the definitions that you're given about things like incremental development. So copy it right here. Incremental development is the process of writing, compiling, and testing a small amount of code, then writing, compiling, and testing a small amount more, an incremental amount, and so on. And so when you're doing that, like that's just the best way to write a program. You can't write a big program all at once, right? Like for example, we do this PyCharm. Okay. So here's something that I was working on, and so I've got two files open here in an editor. This is not Java code, so this is not for this class. But if you look at this, the one on the left is up to about 226 lines, and the one on the right is 124. So we're looking at like 350 or 360 lines of code. You can't type 350 lines of code and then try to run it for the first time. You're just going to fail. Okay. So what you need to do is what it says here. You need to do a small amount of code at a time. For you, where the programs are pretty short anyway, that probably means just a couple of lines of code. Okay. Um, so then, I mean, these are participation activities. Oh, okay, I see. They're trying to walk us through this process of incremental development. So, well, we can look at it. Doesn't hurt. So what we've got here is a Java application, and we'll actually just run it ourselves. So I've talked about this before, but if you want to run this yourself, like in Replit, the first thing you're going to need to do is look at the top and see if there's a line like this, import, because those need to go at the top of your program if you're going to use them. So this one, Java Util Scanner, is for the keyboard scanner for getting keyboard input from the user. So if I copy this and then I go over to this Java application that I just made in Replit, oops, then I can go at the top of this and put that line there. We need it. And then after we do that, I can get the code that's in the middle here. So everything under the class and under the main is where you would want to start copying. And you would want to go not get these last two curly braces. We only want the inside of the main method. So the stuff that I've copied there is the program. And then in here, this middle section is where that goes. So I'll delete what's there now, and then I will copy this code. Okay, so this is the actual code from Zybooks, but now I have it in Replit. And so if I run this, sorry, there's zooming things in my way. If I run this, then over here is where it'll run. And so it says enter your age in years and you put in a number. So like let's say 22, and then it tells you how many days you are old. And the way it's doing that, if we follow the code, is it's asking you to enter your age, right? That's why it printed that out on the screen. It reads a number from the keyboard. That's what the SCNR.nextInt does. We typed in 22. Then it calculates the user age in days by taking user age in years and multiplying by 365. Okay, and that's it. And then it prints it out. So, okay, that's what that does. Now let's go back here and see what's next. So it says, what variable is used for the user's age in years? So we read it. copy paste it. If the user enters a 10, what will the user age years be assigned? Well, 10, right? User age years is going to be whatever you type in. If the user enters 10, what is user age days? User age days is years times 365. So if you multiply 365 by 10, you're going to get 3650. So there you go. And then once that's working, right, they're trying to show you this idea of incremental development where, okay, this is working so far, but what we want to do now is we want to modify the command to do something more complicated. So here it says, considering leap years and calculating age in minutes. And so they tell us what we should do is we should also calculate factor in leap years. So that means instead of just doing each leap year has one extra day, the statement user age days equals user age days plus user age years over 4 adds the number of leap years to user age days. So basically they're saying we can take this line, which is going to take the number that we calculated and add a little bit to it, right? Because every 4 years there's an extra day, and where that would go. So just look at what I have here. If you type in a 22, you get 80/30, right? And this is the calculation that calculates the 80/30. And what they're saying is under that, we can do this because this is gonna calculate the line 14, right? 14 here is gonna calculate the 80/30. And then this line is gonna take the 80/30 and add on your years over 4. So like it'll add an extra like 5 days if you're 22, for example. It's not going to be a perfect calculation, by the way, but that'll do it. So if I run this code now and I type in 22, we're not going to get 80/30. We should get a little bit higher. And we get 80/35. Okay, so but the point is that they got it working first with the 80/30 days, and then this was an extra add-on once the program was already kind of working. And that's the way you want to program, is a little bit at a time, and then you try to run it. Then also they add that we're going to compute the user's age in minutes. And so the way they do that is they add this variable. If we're going to do the age in minutes, they add a variable for that. So up here where your variables are listed, they added user age in minutes. And then below here, they're going to have to calculate it. So like user age minutes, how would you calculate that? And probably the easiest way to do it, I didn't actually read what was written there, but if I was doing this, I would say the way you calculate the age in minutes is you take the age in days, and in one day there are 24 hours, and in 24 hours or in each hour there are 60 minutes. So I would do 24 times 60, and that would be what I put there. And if I look here, they actually do that. And then also they have a command to print that out. I have the commands in a slightly different order than they do, but then they have a separate printout for the minutes. So now, if you type in an age, like 22, then you get the number of days and you get the number of minutes. But we built up to it, right? We didn't start doing all of the code. Okay. Calculating user age in days. The expression user age over years over 4, assume a leap year occurs every 4 years. Yeah, because when you, so like if you have 20, then you divide by 4, you'll get 5. So if you're 20 years old, you've been alive for roughly 4 leap years, um, right? The statement requires parentheses. No, parentheses are not required there because multiplication and division, we follow the order of operations. So if you take a line like this line right here, and then we take the same line, but we take away the parentheses like that. Uh, in the second case, we have user age days plus, and then user age years over 4. But we follow the order of operations, which is like parentheses. Um, so what is it? They say PEMDAS or something like that. Parentheses, exponents, which we don't have any here, multiplication, division, addition, subtraction. And so when we do this, uh, it's going to do the division first before it does addition because we have division before addition. Okay, so the parentheses are not needed. It would do it in the same order. Okay, if the user enters 20, what is user age days after the first assignment? Okay, so remember the way it works is it calculates the days first and then it adds a little bit more. So I'm not going to run it, but the lower number is going to be what it calculates first, and then it is going to add the little bit of extra, the extra couple of days, the leap year days. Okay. And then after they do that, then they're going to estimate the total heartbeats that you've had. Um, and they do that by adding a new variable for how many heartbeats you've had, and also a variable for how many beats per minute your heart beats on average. So if you change that, right, like I can go like 65 or something and get a different answer. So we have those two variables. And then how would you calculate that? Well, I guess I'll just put it in all my calculations here. Um, so the total heartbeats, the way you would calculate it is if you know how old they are in minutes, right? And then you just multiply by how many times their heart beats per minute, which is average beats per minute, like that. And that would calculate how many heartbeats they've had in their life. And then we would need to print that to the screen, which is another print command. I have all my print commands together. They don't do it that way, but there we go. It's taking its time. I feel like it's paused or something. I'm going to stop it and start it again. Well, anyway, I'll just let that go. We'll come back over here. Um, anyway, we'll get something like this if we run it. All right, so which variable is initialized when declared? Initializing means putting a value in it. So if you look at all the variables up here, only average beats per minute is initialized. And also technically the scanner up here is initialized because we have an equals something. So, but only this one out of the ones listed below that. If the user enters 10, what value is held in total heartbeats? I don't know. We just have to run it again. Why is this code not running? I'm gonna back out of this and then come back in here. Oh, now the buttons. It wasn't doing that before. Okay. What's it say? Anyway, it says if the user enters 10. So we'll put in, oh, oops, let me stop. I forgot that I changed that number. It was 72, right? Yeah. All right, so if we run a 10, if we put a 10 in, really slow. Okay, 10, and we get this. Oops. What did we get actually? The 3, 7 something. Wait. Oh, I didn't read the problem. I thought we were being asked like what we get for the total heartbeats, but we're not really because it says if the user enters 10, what value is held in total heartbeats after the statement age user age days equals user age years times 365. And user age days, that line is here, right? And if you look at where total heartbeats is, it's created up here at this line, but then down here we don't use it, 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 we don't use it. We use it here in their code, right? So at the part that I've highlighted, we have never accessed total heartbeats yet. We've never assigned it a value. So it doesn't have a value. Okay. So it says unknown here, but that's I wouldn't really call it unknown. I would say it doesn't have a value at that point. Um, okay. Oh, and then it tells you about integer values have a maximum, right? We learned that in the variables lecture. And the maximum, it goes up to about 2 billion. So they're telling you here that if you put in an age over 57, then it's going to calculate the answer incorrectly. Actually, let's do that. I'm going to run this. And I'm going to put in 60. And if you look, we have just completely the wrong number in there. It's a negative number. And that's because we actually managed to go over the amount that you're allowed to have in an integer. And when you do that, it basically wraps around. So like if the numbers, if you think about the numbers, right? I'm going to make a little like a small list. We go 16, negative 15, negative 14, dot, dot, dot. And then up this way, you go 15 or 14, 15. Um, that'd be as high as it goes. So imagine that this was your list of numbers. And what happens is if you go past 15, then you end up back down here at negative 16 and then keep going up again. And so what's happening here is if I run this code, uh, if I put in, I'm going to put in 57 to see what it does. And I might have to run this like 2 more times. Yeah. So if I put in 56, I'm getting a number that's close to the maximum because it's around 2 billion something. And if you go higher, then then it goes negative. So as soon as I put in the 57, it's negative. And because of that, bad things start happening because now if I were to put in like 100, I'm going to put in like 110. So if you're 110 years old, now we have this number, which is clearly wrong. Um, so you just get wrong answers after a certain point. Okay, here, let me go back here. How many sections do we have? Okay, this is the last section. So now we're on the section on floating point numbers. Um, and I can do like a lecture on this, but I don't want to do too much here. So let me just explain the concept of floating point numbers. So the idea is this. Um, so uh, we are storing numbers in a certain amount of bits. Okay. Like let's just say like 16 bits or 15 bits or something like that. Okay. Um, so like 32 bits or 64 bits or even 16 bits, um, etc. And those are 16 ones or zeros. And so if you imagine um, a 16-bit, um, let's say integer, then what you would have is you would have 1 bit for the sign, and then after that, you would have 15 bits for the actual number. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So 15, and then 1 bit at the beginning is where it stores whether it's a positive number or a negative number. And so the biggest number you can store is actually 2 to the 15th there. Is going to be the biggest. Actually, 2 to the 15th minus 1 is going to be the biggest number that you can store there. And so let me open just kind of oh no, I have a calculator right here. I'll use hand calculator. So if I do 2 to the 15th, I get like 32768. So like the biggest number you can store is going to be plus 32768. And the smallest number you can store is going to be actually 7. And the smallest is going to be negative 32768. Uh, that's going to be the biggest number that you can store. And then if you want to store a decimal number, like let's say, I don't know, um, like 30 point, 325 or something like that, then what you have to do is you have to give up some of these bits if you wanted to do what we call fixed point. Um, you would have to separate some bits out to use for the fraction part, right? So you would have some bits used for the beginning part and some bits used for the part that comes after the decimal point. And that's what we would call fixed point arithmetic, so, or a fixed point number, the fraction part. So maybe you would do this. So maybe you would do 10 bits for the like the integer portion or the whole number portion, and then and then 6 more bits for the fraction, right? Uh, depending on how much precision you needed there, maybe 6 bits, for example. But then what you would be limiting yourself into is that you've only got 10 bits for the whole number now. So you would actually be limited to now, if I go 2 to the 9th, because again, we still need 1 bit for the sign. We would end up going from negative 512 up to um, positive 511, but we would be allowed to have 6 bits for fractions, which I mean I'm not going to really um, work that out, but you would have a couple of you know some digits over here represented in this 6 bits. But the point is that you if you're saving bits off to use for the fraction part, then you lose bits for the rest of it, which means that your range goes down. And so in this fixed bits, I'll say fixed decimal point scheme, we lose like, well, I'll say this, we gain the ability to do fractions, but we limit like the size of the values because now we're limited to negative 512 to positive 511 when we used to be able to go from negative 32,000 up to positive 32,000, right? Because we lost 6 bits for the number part. So we gain the ability to do fractions, but we limit the max value we can store in the number of bits that we have. And so they didn't like this. So they came up with another way to handle decimal numbers called floating point numbers. Um, so this isn't great. So people came up with floating point numbers instead of fixed point. So what I set up here was like a fixed point scheme. So floating point numbers don't do it that way. They basically use scientific notation. So basically what they do is this. They say, we store numbers like this. So we have a beginning part. I don't want a 3 there. It makes it look like I'm trying to write pi or something. And then times 10 to the, and then you have numbers over there, right? And then, so we store them in scientific notation, basically. And then what we've got is there is a certain number of bits for this side, and then there's a certain number of bits for the exponent, okay? The bits that we have are split between the what we call the mantissa and the exponent, okay? Um, so this is the mantissa, and over here, this is the exponent. Now, what I said there was kind of a lie in the sense that numbers are binary numbers, and so they're stored, it's not actually times 10 to the anything, it's times 2 to the something. And also there's other details that we didn't talk about, like we always know that this is a 1 because it's either a 0 or a 1 in binary numbers. So we know it always will start with a 1. And if it's always going to start with a 1, then you don't even need to write it. And so on. So there's kind of details that we're not going to talk about in this class. But this idea that floating point numbers are stored in basically scientific notation, and you have a certain number of bits here and a certain number of bits here, that's the key. And you can look this up. Either they will, they may list it here. Just going to scroll down and see if I see it. I don't. So I guess I'm going into more detail than they want here. But if you care about this, um, if you do like double and then like mantissa bits, like that kind of thing, and you Google it, you'll see exactly how it's stored. Because we're going to be using doubles for our decimal numbers in this class. And this has been standard for a long time. And so go here. I mean, probably we want to not just have that. We probably want maybe Wikipedia here for the standard. And so here's a picture. So you can see like how the bits are used. In a double, we have 64 bits. And so the sign bit, we need 1 bit to say whether it's positive or negative. And then you'll see it says 1 point, which is how I said it was. We know it's a 1. And then we have all of these numbers. That's what they called the fraction here, but that's the it's this part. But like think of it as like zeros and ones. So there's like 52 of those. Um, and then over here we have 2 to the um, biased exponent e. Okay, so it gets complicated, but the exponent um, is going to be stored in 11 bits. Anyway, like the details don't matter, but like if you care, this is how it's stored. Okay, and they are complicated, and we don't do much with them, but you can always look it up if you care about how it's stored. Anyway, so we have those. What do we actually need to know? So here's what we need to know. So we use in Java uh, doubles for all of our floating point stuff. There is float as well. That's another type, but we're not going to use it. So we use double for all of our floating point numbers. Kind of, that's the standard, okay? It's not the only type, but we do. So to declare one, so to declare a double, you simply say double, and then you put the name here. So like my variable, like that. So just like you would for an integer, but it says double, not int. To initialize it, well, you could do it on 2 lines, where first you would initialize it, and then after, sorry, you declare it, and after it's declared, then you can type in the number, right? Like there's a number, something like that. Or you can combine those into one step and just say like double my variable equals whatever you want. Okay, um, so you declare them basically the way you do integers, but they're called doubles because they're going to have decimal numbers in them. Okay, now what else can I say about that? One thing that you need to be careful of, it will cause you trouble if you don't do this. So be careful. Um, always, always use a decimal point when writing numbers to make sure the compiler knows to do decimal arithmetic and not integer arithmetic. What's that mean? I mean this. If I go here, if I do this, double x equals, and I do this, this is going to give me the wrong answer. I'll get 3. I'll get 3 from this calculation. If I do this, I'll get 3.5, which is correct. Okay? So this is the wrong answer. This is the right answer. And the reason is because when Java sees 7 over 2, it's going to do integer arithmetic. And we know that 7 over 2 is going to be 3.5, but because it thinks that it's doing an integer calculation, there's no fractions, it's going to cut the 0.5 off and just leave you with the 3. And then the 3 is going to be stored in the variable x, and you'll have it, it'll be a double, it's a decimal number, but it'll be 3.0. So you have to be careful. They'll tell you that, but I'll tell you that too. Um, when you're writing any numbers around doubles, make sure you put like a 0.0 on them. Technically, you can just do that, like only one of them needs the point. Technically, if you do this, this will work. Just any decimal point anywhere will make it do the calculation correctly, but it's just better to type it in this way. Okay, so that said, let's look at this. So they will say, So we got double, we got another double, we got another double. And another thing that you need to know is that now to read a double from the keyboard, there's a different command, right? So um, let's see, to read an integer from the keyboard, you've been doing this, right? You do like, I'll say my variable is, and we know that you do scnr dot next capital INT, like that, to read a double from the keyboard. So a user can type it in. It would be, now I'm using the same variable name, but obviously you would, this one won't be the same as this one, right? Because this one's got to be an integer and this one's got to be a double. But um, to read a double, next capital D on double, like that. So it's not harder. You just have to remember to read an integer, you do next int. To read a double, you do next double. Okay, so looking at this code, they read in a double. They do a calculation. Notice that they put the 0.0 on the end, like I said you're supposed to, and then they printed them out. Okay, so there's not a lot to do here. Declare a double, double, and it's supposed to be called person height, right? So just like you do for integers, uh, declare a double variable named package weight and initialize it to 7.1, right? Um, anyway, so looking at these, which statement best declares and initializes the double variable? I mean, this is wrong. Why is there a percent sign there? The last one is wrong because they didn't put the 0.0 like I said you're supposed to. So it's the middle one. See, floating point literal should have a fractional part. Literal just means you're typing it in. All right, which statement best assigns the variable? Both are doubles. Again, the difference between them is the bottom one put the 0.0 like you're supposed to. All right. What about these? I think they're both okay, but it's like the last one looks right. They say best to have that. All right. And yeah, so this is kind of an interesting thing. And that's all it is an interesting thing. But so obviously you're going to use integers for integers and doubles for any time you want decimals. And you'll probably in this class we're just going to use doubles for money as well typically. But there's actually reasons not to use doubles for money because doubles are not uh, very precise. They have about 16 digits of precision. Um, so so you can have two numbers that are supposed to be the same and they're not quite the same because of the imprecision. Okay. And so normally what they do for money, or if you're being very careful about it, then instead of using a double, you should just use integers, or maybe probably something bigger than an integer, but integer types, and you would count up cents instead of dollars, right? Because there's no such thing as a half a cent. There's only 1 cent is the smallest denomination of cents. So, they just have a comment here about there are kind of some issues with talking about money in using floating points there. And then they just ask you a couple questions like uh, if you were counting cars, you would use an integer. If you're talking about temperature, you'd probably use a double because you can have a half a degree. Person's height in centimeters. Well, if you're measuring half centimeters, you would want double, or quarter centimeters, 100 and, 85.36 centimeters. The number of hairs on somebody's head, that would be an integer. The average number of kids per household. If it's average, it's probably going to be like 2.5 or something, right? So since it's an average. Okay. Um, you have infinities and not in numbers. And basically, in doubles or with doubles, um, a number over zero is infinity. Can be also a minus infinity if the number is negative. Um, and infinity over infinity or 0 over 0 is NaN, which means not a number. So we have to have these because you know you're not allowed to divide by 0, but what happens if you do? And so if you do, you get infinity. Okay. And and infinity over infinity doesn't make sense, and 0 over 0 doesn't make sense. So they have this extra value called NaN this way, which means not a number, to say something went wrong. So if you do like 13 over 3, that's fine. You get a decimal. If you do 0 over 5, that's also fine. You can have a 0 on the top, you get 0. 12 over 0, that's not allowed. What will happen is you'll get infinity. And if you do 0 over 0, that's not a number. Um, okay, so we are out of time. Well, okay, let me talk for 1 minute more. Um, so we'll see this soon for how to use this. It's a little bit tricky to get into now. Um, but basically, we've used this print command, system.out.print, and then like you put stuff here, and you can put like a variable there, for example. We've used system.out.print line. So I could say like, I'll do this actually, like that. Um, Makes sense. And you can do the same thing with a print line. But if you do that with a double, then you can't really get control over how that's being printed out. So I'll just show you. I'll go to here. I'm going to delete everything in here. Everything in here. So like if I just do double, and I'm going to say 7 over 6, like that. And then I'm going to do system dot out dot print line double, sorry, x equals. And then I'm going to say x is, and leave space, and then I'm going to do plus x. Okay, now when I run this, you'll see that what happens is, when we get it, there we go. Oh, haha, see, look, I just made the mistake I told you not to make. Got to put the point zeros on the end to get the right answer. Okay, so you see how it's printing. X is 1.1 and then just huge number of sixes at the end. Um, that's what happens sometimes with doubles. And a lot of times you don't want it to print that way. You want to control over how it's going to print out. And so in order to do that, what you'll do is there's another print command you can do called printf. So it's printf. And the F is for formatted. Print formatted string is what that's for. And so you would actually do this differently. What you would type is you would type the number X is, and instead of just ending it there and then putting the X on the end, you actually put in a symbol here. And so you put a symbol like this, like %F, and what that means is this is where I want the number to go. And then after you close the string, right, with a double quote to end the string, then you put a comma and then you put an X in like that. And so this is the kind of command you would use. Now, if I do this here, I'll put a semicolon at the end, then um, we'll just get kind of, we're not using the control that we have over it, but you know, it printed the number x is 1.16667. So now it's like a smaller number there of digits being shown. But the point is that I actually have more control over it because what you can do, and they explain it here, is that percent %f that I put there. Where do they show it? Yeah, so how I have a percent %f here, you can put before the f, you can put like 0.2, for example. So this looks kind of complicated, percent %0.2f, and that would mean round it to 2 decimal places. So if I go to the code that I have here and I change that percent %f to percent %0.2f, and then I run this, you see it says, well, it's printing weird. Okay, there, well, now it's gone. I don't know what I just did. Um, but it's controlling the number of digits. Also, you can't really tell it here, but one issue with printf is that printf works like print. So on print, you know how it doesn't go down to the next line. Printf also doesn't go down to the next line when it's done. And so to end it, you should have one of these. You just put a \n on the end. That means new line. So I mean that's a lot of information real quick at you, but like do \n, and then I run this. Um, you can see the number x is 1.17, and you can use this to control like how your numbers look better. So like if I said, well, I need more than 2, but I don't want that many, how about 0.4, right? So you can just change that percent %0.4f, and you can get it exactly the number of digits that you want. I don't know what's happening with the font over here though. But anyway, that's what they're talking about here in this section. So they're showing it right here, how to do that. And this is an example with 4 digits. So like they're just asking you how to do it. So it says, what if I want to print um, 2 digits after the decimal point? And they're just saying, well, which one of these is right? And it's this last one, percent %0.2f. So they just can you get it in the right order? Um, what is output by this? So they say percent %0.1f. So 0.1 means 1 decimal point, and it will round it. So if you round this to 1 decimal point, you would get this middle one. And then here it's percent %3f, so that's 3 after the decimal point, so that's 9.135. And so it's 135, but this will actually round. It doesn't just cut it off. So it won't print 135, it will print 136 because the next digit's a 7, so it'll round up. Okay, so we didn't do this last one, and we're out of time. So I'll probably talk about this Monday. You still have a long time to do this assignment, but we're done for now. I'll talk to you guys later. Gotta go.